In this video, I want to talk about how the normal approximation can be used to approximate probabilities that are ordinarily found with a binomial distribution. In this problem, a gambler bets repeatedly on roulette, betting on red. The chance of winning is 9 out of 19. Suppose that the gambler plays the game 100 times. Use the normal approximation to estimate the probability that the gambler wins more than 50 times. So let k be the count of the number of times that the gambler wins. So the question is asking for the probability that k is strictly greater than 50. I get a count that's bigger than 50. Now the exact answer can be found using the binomial distribution. More on that in a second. But an approximate answer can be found by using the bell curve. To do this, we first have to convert to standard units, and to convert to standard units, we first need to get the expected value and also the standard deviation. So let's find the expected value and the standard deviation. So the expected value of a binomial distribution is equal to, let's see, where's the cursor? There it is. The expected value is equal to mu is equal to n times pi. So here I'm doing something 100 times, and the probability of success is 9 over 19. The standard deviation is equal to the square root of n times pi times 1 minus pi. That's from the formulas for a binomial distribution. So for this problem, that would be equal to the square root of 100 times 9 over 19. If I get the 9 out, times 10 over 19. Okay, so I will do those calculations in Excel so that we can see them. So the mean works out to be 100 times 9 over 19, so about 47.37. And the standard deviation works out to be the square root of 100 times 9 over 19 times 1 minus 9 over 19. And so I get something that's slightly less than 5. So if we play the game, we expect to have 47 successes, give or take 5 or so. Okay, so now I need to convert to standard units. So to convert to standard units, this probability will be approximately equal to the probability that, and let me get rid of these calculations now that we've already done it, so I don't need this again. The values are on the screen. That's going to be the probability that a random variable that's normal is going to be bigger than or equal to something. Now, I have to make what's called a continuity correction. I only do this continuity correction because this is an approximation of a binomial distribution. For example, for the height problems that are in the other two videos in this series, there was no need to do a 0.5 adjustment. However, because I'm approximating something that's binomial with something that's normal, I need to make an adjustment. Now, how do I figure out how to make this adjustment? Well, the easiest way is to just draw a quick picture to see which way the pattern should go. So here I pretend that this is the histogram for the binomial distribution, 50, 51, 52. And the area in question is going to be things that are bigger than 50. So this rectangle and this rectangle, but I don't shade the rectangle on 50. So the cutoff is going to be right here at 50.5. So I need to convert 50.5 into standard units. And let me bring that down a little bit, 50.5. And I emphasize again that this 0.5 addition, or perhaps subtraction depending on the problem, is only necessary because I'm approximating a binomial distribution by a normal distribution. The next step is now to convert to standard units using the mean and the standard deviation that were found earlier. So 50.5 minus the mean of 47.368 divided by 4.993. And so this will give you my z-value equals 50.5 minus the mean divided by the standard deviation, and I get the z-value of 0.627. So the probability that a normal random variable, standard normal random variable, is bigger than 0.627185. Now this probability can be found with Excel. So the probability of this event happening would be equal to 1 minus norm s dist of 0.62, well, let me just type in B3. 1 minus norm s dist of 0.627. To see the picture for this, let me get rid of this little cartoon here. Whoops. Let me get rid of this little cartoon here and draw what the picture looks like. We need to find the area to the right of 0.627. Ordinarily, the norm s dist command returns the area to the left. And so because in this problem I want the area to the right, I need 1 minus norm s dist. This would be the same story if I use the table that can be found in the textbook that returns areas to the left. Because this one is an area to the right, I need to take 1 minus norm s dist. So the area that's shaded I get by hitting enter here. And so I get the probability of 0.2653, rounding it off to 4 decimal places. So there's about a 26.5% chance of coming out ahead by winning more than 50 times. So that's the way the problem goes here. Let me show you how to do the same calculation using a calculator. So for the calculator, it would be a second distribution, normal CDF, and then for the calculator I have to put in a left endpoint and a right endpoint. So 0.627185 would be the left endpoint. That's the left endpoint. For the right endpoint, I basically want to put infinity. So I'll put in some really big number. I'll choose 10 to the 99, but some really, really big number so that I get the area to the left of 0.627. And I get the same answer, 0.265269. That matches what you see here from Excel. So that is how to use the calculator to find the area to the right. You should basically just use 10 to the 99 or negative 10 to the 99 as either the right endpoint or the left endpoint, respectively. But to conclude, I want to say that this is an approximate answer because this is approximate because I use the normal distribution. If I wanted to find the exact answer, the way I would get the exact answer would be 1 minus binom dist. Binom dist, 50, 100, 9/19 true. Just like we did with hypothesis testing. If I want the chance of more than 50 successes, that's 1 minus the chance of 50 successes or less. So the probability of more than 50 successes, the probability of more than 50 successes will be 1 minus the probability of less than or equal to 50 successes. So this would be the exact answer, and notice that is very, very close indeed to the approximate answer that was obtained by the normal distribution. So all this to say, the bell curve, it can be a very good approximation to the normal distribution, and this approximation works if n, well, as is used, is if n is at least 30, if n times pi is at least equal to 5, and n times 1 minus pi is at least equal to 5. And we had all those conditions for this problem. If I take, let me get rid of the picture here. In my problem here, we had that n was equal to 100. That was more than 30, so the bell curve, that part of the assumptions were satisfied. N times pi, the average worked out to be about 47.3, and that was plenty more than 5. And also, if you compute it, n times 1 minus pi works out to be about 52.7. And that's also plenty more than 5. So all three assumptions about when to use the normal approximation for the binomial distribution applied, and so we get a very good fit for the approximate answer versus the exact answer.